what we're here to talk about is the alpha Laval capacitive load cells. I'm not sure if the audio was on when we started this, but again, this is Jim Bodel with Acuity Process in North Attleboro, Massachusetts. If you have questions, again, please go ahead and click that Q&A button on the bottom, and I'll get to them as I can. So basically, what we're here to talk about today is the basics of load cells. We're going to focus on the alpha Laval capacitive system, but in order to fully explain that, I think it's really important that we understand the nuances of how a load cell functions, and that'll help you understand why the alpha Laval system is different and we think a little bit better than some of the other technologies that are out there. We're going to run through some of the benefits to the end user. We'll talk a little bit about how you go through a selection of one and what kind of things you need to consider as you do an installation of one of these systems. So without further ado, we'll get started. And we're going to talk a little bit, as I said, about load cell basics. So this is really important. And if you look at the picture on the bottom, which I actually think is kind of humorous, the guy looks a little bit like I do, but you'll notice that regardless of whose load cell you're considering, whether it's an alpha Laval system, whether it's a shear beam style, a compression style, a capacitance unit like ours, a strain gauge system like others have, they all function in the same way. And if you look at this picture, you'll see to the left that there's a fixed portion of the cell where the cell is anchored to a point. Well, that could be the floor, that could be a frame member on a skid, it could be a deck in a pharmaceutical plant. And if you look to the right, you'll notice that there's a load that's on the end of the measuring cell. So as that load changes, as you look at the cell beam, you'll notice that the cell is actually deflecting a little bit in this area. Okay, you can see it right in here. And regardless of how the cell is configured, that deflection is the same. In other words, if I have a ring style load cell or a beam style load cell, and again, I'm going to drop out of this just for a sec to show you what I'm talking about. But if you look here, this is a beam style load cell, excuse me, and you would have a fixed element here. You'd have your load sitting on this end. Okay, that's one style. This is a compression style load cell where this would be sitting on a fixed location, whether it be a floor, and your actual dynamic load would be sitting on the point here. Okay, but let me jump back into that presentation. But you'll see here that as that load changes, the actual frame member of the beam bends, and as it bends, we measure that deflection. That deflection gets measured and then is translated into an electrical signal that can be read by some sort of a measuring unit to translate into a weight measurement. Okay, and again, it's important to understand that this is true whether it's a compression style load cell, whether it's a beam style load cell, sliding beam, shear beam, single point, it's always the same. What's different between styles of cells is how we measure that deflection, okay? And that's really important. This is always the same, it's how we measure it that's different, okay? I gotta click to the next slide. So most everybody in this industry knows of what's called a strain gauge load cell. And strain gauge load cells, just like we talked about a minute ago, take a load, and as that load changes, you'll see it right down here in the middle of the slide, the beam deflects. In a strain gauge load cell, they use something, it's not important that you know this, but it's called a Wheatstone bridge circuit that's adhered to the side of the load cell. And as that beam deflects, the shape of the Wheatstone bridge changes, and it changes the electrical resistance across that bridge. Measuring the change in electrical resistance gives you a subsequent, the ability, to measure weight. And you'll see here, there are some issues in a strain gauge style cell. As I mentioned just a minute ago, that strain gauge is actually adhered, and you can see it a little better in this picture right in this area here. It's adhered to the cell. And as that cell bends, the actual strain gauge unit itself is bent, is actually deflected with the beam to change the load rating. So think about that. As the thing is deflected, it's subject to a lot of the same loads that the cell itself, the beam, the metallic beam, is subject to, and that's something to consider, okay? Some other issues with these. The strain gauge unit, as it moves, creates very small changes in voltage, and that means that the change has to be amplified in order to travel to the converter. And also, in a strain gauge load cell, that's an analog signal. It's a resistance change, which is an analog signal, and it needs to be converted to a digital signal within the converter before it can be read by the system. So a couple of things to think about with a strain gauge. Again, as we mentioned, they're adhered to the cell, and actually they're pretty delicate, as I note up here. They don't like to be overloaded. Okay, so if you overload a strain gauge cell, and pretty commonly you'll see overloads in the 1.5 times working capacity range. If you exceed 1.5 times working capacity range, you can damage the strain gauge unit. In addition, strain gauge cells don't like to be side loaded. They don't like to see loads outside of the plane of the normal weight that they're trying to measure, nor do they like torsional or twisting forces, because any of those type of things can irreparably harm the actual strain gauge sensor unit. They're also sensitive to welding, because if you think about it, you've got the strain gauge unit adhered to the metallic beam, and if you're welding on a system that has one of these, the actual strain gauge itself can see the welding voltages and cause damage to the cell. In addition, because they create an analog signal, they're sensitive to ambient electric noise, otherwise known as EMC. So if you've got a variable speed drive in close proximity to a strain gauge load cell system, that can actually get picked up by the analog wiring and translated to the system and cause problems in readings. And finally, there's a statement here, and I actually took it from a website called LoadStarSensors.com, and they make strain gauge load cells. And it says that one of the challenges with this is that they've got to amplify the signal, and then they've got to put it through a converter to create a digital signal for the readout or the PLC. And when you do that, converting from analog to digital, you got the potential to add some error in that conversion. This is also a big issue with strain gauge load cells. You'll note here, we just talked about the fact that the units themselves don't like to be overloaded. They don't like to be twisted. They don't like to be subject to side loads. Any kind of a shock load is difficult for a strain gauge. So what do we do about that? If you're going to employ a strain gauge load cell, you've got to put some ancillary equipment around the strain gauge in order to protect it from being subject to that load. So what you're looking at here is basically a mounting kit that you can purchase from the strain gauge manufacturer, or in some cases people manufacture these themselves, but the concept is the same. This actual bracketry that you see around it is designed such that any kind of a load that's out of the normal weighing plane, and think about the normal weighing plane is going to be pushing down directly on this top plate. This would be your fixed plate on the bottom. Okay, and the cell is inside here, and it's actually free floating. It's not physically attached to the top or bottom. But basically, this whole thing is designed so that the load that the cell sees is in a fully vertical direction. Any kind of a side load in this particular installation would get picked up by these turnbuckles that you see right here. Any kind of an overload would get picked up by these travel stops that you're seeing right here. These are adjustable, as you see. This one also has liftoff protection that you'll see here so that the vessel can't come off the top of the unit. But again, this whole system is designed to protect that load cell from seeing loads in a direction that it can't tolerate. So, that being said, strain gauge load cells probably make up, if I had to guess, 85% of the marketplace. They're significantly large players in the market. Everybody recognizes a lot of the large brand names. They've been around for a long time. What I want to talk to you about now is capacitance measurement. Remember we talked earlier about the guy on the diving board and the deflection. With a strain gauge cell, as we just mentioned, the strain gauge itself measures the deflection because it's deflected as the load changes on the cell. Well, Years back, capacitance measurement technologies were invented, and they've been around for quite some time. What's interesting is in the US, and particularly in the sanitary, biotech, pharmaceutical, food processing segment, they didn't really make it to the United States until 2013, 2014. But the technology's been around since the early 1970s. And it was developed originally for industrial applications where substantial loads, shock loads, things like that were beyond the capability of strain gauge technology. What's interesting is it's been adapted, as I said recently, to the sanitary segments because it's got some real value for our clients, and we're going to talk a little bit about that. So this is really the meat and potatoes of the presentation right here, folks. If you look to the right, we just talked about this, and this is a great graphic representation of what's going on in a strain gauge load cell. If you can envision, you've got, this is your beam, we call it. This is your fixed end here on the bottom left, and this is your force as your weight is applied to it. This beam frame is deflected. As I mentioned to you earlier, that you'll see these strain gauge elements which are attached, and the four of them form what's called that Wheatstone bridge circuit. They're all used in concert to measure resistance change as the frame is bent. Okay, and you can see if I load the heck out of this on the bottom right-hand side picture, you can envision that that sensing mechanism is subject to that load as well. If you look over to the left-hand side, though, here's what we're going to talk about today, and this is called the capacitance measurement system. Same thing's happening. The beam is deflecting, just like we talked about with the strain gauge unit. But what's different, and this is really important, and again, this is kind of proprietary technology, but there's an element that's suspended inside the cell, and there are ceramic sensing units that are adhered to that element, and what they're going to measure is a proximity change from the adjacent surface of the cell as it deflects. So think about, you see this air gap inside of here. As the cell is deflected, these elements are capable of measuring a distance change between those two surfaces. You'll see here, as the cell is deformed, the hole becomes oblong, and those distances change, as do these distances. That cell is able to measure that distance change and then translate that into a weight measurement. This is kind of important. Think about something. On the strain gauge side, we're subjecting the sensing element to the load. In this side, we're not. The sensing element never sees the load change on the beam. The only time it would see it is if you exceed the elastic limit of the beam itself and it failed. Then it would contact the load cell sensor. So this is really important. And again, I showed you two different types of cells. And I'll go back and show you that again. If you look here, this is a compression or a ring style cell. It's harder to understand in this cell, but the same concept happens. As you apply load to the top surface of the cell, this entire surface is deflected down inside the body, and it's measuring a distance change inside compared to the adjacent ceramic sensor. It's easier to understand with this one because you can simply see that as you deflect the cell, you can envision how this is able to measure the deflection. But the concept is the same between the both of them. They measure that internally. Okay, I hope that's clear. If it's not, please let me know. I'm going to share my screen again here. So, bear with me. Okay. So what's interesting about this technology, and this is really what's the meat and potatoes, and that's spelled wrong, I apologize. It's not deflection, it's deflection. But our technology means that the sensor is not in contact with the beam cell body. It never sees the bending, torsional side loads. As long as you don't overload the cell itself, only the robust metallic body of the cell is affected. So some of this is proprietary, and Alpha does not share this extreme details, but this is all done by measuring a difference in a capacitor discharge within the cell. And it's measured over a period of time, and it's done in picoseconds, which are extremely small periods of time. So this thing is able to measure that distance change extremely accurately and extremely quickly. And what's also interesting is that the cell itself, within the body of the cell, all of the smarts of the system are inside the cell. So it's measuring that capacitive change, and it's creating a digital signal within the cell body itself instantly. There is no amplification. There's no analog to digital converter required. There's no additional error required, right? That's really interesting. If you think about a strain gauge system, a strain gauge is a relatively, for lack of a better word, kind of a dumb system. It doesn't do anything until you introduce voltage to it, excitation voltage, and measure change in that voltage. This system actually creates a digital signal out of it. You can actually read weight directly out of one of these cells because the signal is created right in the cell, okay? So what does that mean to an end user? All right, simple. It means reliability, because if you're going to overstress a strain gauge cell, you need to be ready for it to be out of calibration or fail. You have to worry about more frequent calibration. One of the other things that our clients particularly like is the fact that with a strain gauge cell, you require all that mounting kit equipment that we showed you earlier in the presentation. With ours, you don't. You don't need to protect our load cell against overload, so it doesn't require all of that additional mounting equipment. What's that mean? That mounting equipment is very difficult to clean. Okay, imagine if you're doing wash down in a pharmaceutical plant and you're washing down that area. There's a lot of threads on those turnbuckles. There's a lot of area that's difficult to get to. None of that exists with an Alfa Laval system. And these are extremely low maintenance systems, where on a mounting kit oriented strain gauge, you need to maintain that mounting kit, lubricate it, be sure it's an adjustment. Those aren't required with an Alfa Laval system. I'm looking for something as I'm talking here, and I don't know what I've done with it. Oh, here it is. So I want to show you something, if you can bear with me and pardon my ignorance. But this is as simple as it is to install an Alfa Laval load cell. If you can imagine, and I'm going to show you, it's going to be a little shaky here, but I want to show you something. I've actually got a system sitting next to me that shows the installation of a strain gauge cell. And I know this is probably a little difficult to see, and I'm a little shaky, okay? But take a look here, and you can see that the cell itself is bolted down to a mounting block that would be welded to the frame. This is the mounting kit that would be welded to the bottom of your live load, and that's all that's required, right? You don't need any other equipment. This kit has a flexible mounting bushing on it that allows that unit to be slightly out of alignment and still maintain accuracy. So even if you have side loads or shock loads, right, this unit is capable of handling that without any concern. I hope you folks could see that, and I think somebody's asking me a question. Bear with me. Let's see. It's clear. Thank you very much for the comment. So let me bring back my presentation here if I can find it. There it is. All right. So again, what are the features and benefits that matter here? Reliability, the hygienic installation, and the fact that we're not concerned about maintenance, okay? In addition, this is another important feature, and this comes into play. We'll talk a bit about that. This sensor is much more sensitive than a strain gauge. What does that mean? It means that it can measure smaller degrees of change accurately than a strain gauge can. So what that means to us is that the beam itself does not have to deform as much to get an accurate measurement. In other words, if you have a sensor that's less sensitive, you have to deflect the beam further in order to achieve a measurement. With this unit, because the capacitive sensor is more accurate, it bends less. So overall travel on an Alfa Laval system is usually 2 to 3 times less than we find in a comparable strain gauge unit. That's important. It can be important because if you think about it, that allows us to have a more robust beam. It's not required to bend as far. It can be heavier gauge and capable of handling that deflection. So in addition, that heavier beam gives you more shock resistance and overload capability, which can be as much as 10 times more than the gauge is rated for. So in other words, if I have a 1,000 kilogram cell, I can overload that to 10,000 kilograms without damage. If I have a strain gauge system, typically it's 1.5 times operating load. Ours has a significantly higher side load tolerance. It can handle up to 500% of its rated capacity in a side load. So again, we don't need any mounting protection. Where is this important? Think about something. In our business, if we have mobile units, like we've got a lot of clients that have mobile weighing or mobile carts, and they want to employ like in the pharma business, let's say you have a cart that has got a disposable bag in it. You want to measure the liquid volume in that disposable bag. The challenge is you can't use conventional methods to measure the liquid volume because the bag is irregularly shaped. So we use, or they use, weight. Provided you know the specific gravity of the liquid, you can calculate the volume of the liquid that's in there. But now think about something. If you've got a cart that you're rolling down a hall, let's say it's a 500 liter cart, which has 500 kilograms of load in it. That's a lot of weight. And then the cart itself may weigh another 100 kilograms, so 600 kilograms. If you're rolling that down a hall and you bump into something, there's a tremendous amount of load, deceleration load that happens when the cart stops. If you're using a strain gauge load cell under that cart, the strain gauge would be subject to that deceleration load, and you'd have to protect it with some sort of a mounting kit. Ours, you wouldn't. And then if you think about if you're pushing the cart around with the strain gauge lockout or strain gauge protection kit on it, you've got to make sure that when you bring the thing to stop, that you haven't bound the kit up and that the cell is still able to move freely. You don't need to worry about that with an Alfa Laval system. Hope that's clear. Look, I got a question here, so let me see. So somebody just asked me, what about a mobile application? So I hope that's answered the question. Basically the mobile, this question was by Nate, I think it is. The mobile cart considerations are, you've got to size the cell to handle the dynamic load that's in the cart or bag. You've got to account for the overall weight of the cart itself that's going to be sitting on the cells. But again, with our unit, you don't have to be concerned about damaging the cells due to shock or vibration that's common when you're pushing around a heavy cart. I hope that helps answers your question. Somebody else? He just asked again, they're having issues with mobile carts. How difficult, I apologize, I don't have my reading glasses, I'm trying to see this. How difficult is it to retrofit existing systems? It's an interesting question. We've actually done a fair amount of retrofitting of existing systems where people have had trouble with exactly what we talked about. We have the capability, we've got some subcontractors that we work with that can help you to remove the existing system and put an Alfa Laval system in if you'd like. It's actually relatively straightforward. So I'm going to go back to sharing again here. I think we've finished this slide. So there's a couple other things that are really interesting about the Alfa system. I told you earlier that it has the smarts or the intelligence is in the load cell. So what does that mean? The cell itself can actually be pre-calibrated at the factory and come with a factory certification on it. You can't do that with the strain gauge load cell. There's no way, because there's no intelligence in the cell itself. It's a redundant opportunity to be sure that the system has met third-party calibration. Excuse me. In addition, there's another thing that's pretty cool about this system. Think about an analog strain gauge system. When you have a strain gauge, it's measuring a resistance change. And what does that mean? It means that the length of the wire that's attached to the cell has an impact on the resistance that the system sees. In other words, in a strain gauge, I'm going to be measuring the resistance change in the gauge itself. In order to do that, I've got to know what the resistance in the wire that it's connected to is, right? And if I change that wire, or I cut that wire, or I modify that wire, I've got to recalibrate the system because I've changed the resistance because I may have changed the length. Not true with a capacitive system. Remember, this guy develops a digital signal inside the cell, and it's transmitting a digital signal out of it. We have a very simple coaxial cable that comes out of the cell and has a connection that can be easily removed. So if this cell was ever damaged, you could simply remove the cell, thread a new one in like this, make a new connection on the other end. And I don't, maybe I do. Let me see if I have one. I don't know if I do. I thought I did, but I don't. This is a regular coaxial cable here, and it utilizes a regular old BNC connector right here, okay? This connector can be put on, the cable can be cut to any length that you want, and you can install the connector at any length you want, making for a neater installation, and it doesn't affect the performance of the cell itself at all. It's a digital signal. That's really an important feature. So let me jump back here again. So again, the load cells can be changed on site because it's digital signal. The calibration doesn't change. One of the other things that's needed, the signal itself is a lot stronger. A digital signal is a lot stronger than an analog signal, which means that I can travel longer distances. We can run these cables up to 100 meters away with no effect on performance. In addition, the cells themselves, because we talked about the sensing element is not in contact with the metallic case of the unit, you can weld on a frame that has our cells mounted and not worry about damaging the cell. You have to disconnect the electronics around it because you can fry the boards inside the controller if they're not electrically isolated, but the cell itself can stay on the skid. That's a big deal because if you have a heavy vessel sitting on top of a strain gauge cell, you have to remove the strain gauge before you weld on the frame. Ours are less susceptible to radio interference, any kind of electrical interference. And one of the things that's also important is if you consider a strain gauge system, they function with something called a summing box. And what that summing box does is takes those 3 analog signals in or 4, however many cells you have, takes those wires and takes them in and converts them to digital in the junction, in the summing box it's called. We don't have that. We have a junction box because we've got to have a place to bring all 4 wires in, but all it is a place to bring the 4 digital signals in. What's really cool is that our display can actually see all 4 cells individually, and I can see each individual weight range. Why is that important? Think about if I have a system that I'm trying to troubleshoot. I'm not going to go through this today, but you can see this is the display unit of the system. This is what I just told you is the digital junction box. Doesn't perform any function. It's just a junction box, and here are the cells. If I had a problem on my system with an Alpha Laval unit, I could take this back to the main screen and I would be able to see what each individual cell is doing. And I could then decide if I've got a problem with which individual cell I've got a problem with, right? So let's see, I'll just show you real quick and we'll keep back to the presentation. This is showing me each cell, 0, 1, and 2. I don't know if you can see that or not. But as you see on the 0, 1, and 2, if I press on one of the cells, I can see that load change on the individual cell. That's a big deal for maintenance people. It makes it a lot easier for them to figure out what's going on in the system, okay? So let's jump back in here. I'm trying to keep this thing relatively fast-paced. So how is the system configured? I just showed you. We've got a weighing terminal right here, which is the microprocessor that controls the system. We've got a weighing module, which is the terminal where the 4 load cells would connect. And we can plug compression-style load cells, beam-style load cells, or single-point load cells into the system. It's that simple. It's a modular system, so you can combine different load cells. You can have 3 cells, 4 cells, 2 cells. In this case, this would be a single unit where in this single box we would have the weighing terminal and the weighing module in the same box. We've got clients that don't like that. They want a smaller box for this. We can separate the units. We're very flexible in how we can configure them. So again, if you look here, we can talk through how you get to selection. Why does somebody use a beam cell versus a compression cell? A lot has to do with the actual measuring range, okay? A beam cell can be limited because of the physical construction of it. You have to be careful not to, it can't handle extremely high loads. Our beam cells, our standard hygienic beam cells, stop at 1,000 kilograms per cell. So with a 4-cell system, you could have 4,000 kilograms. The compression cell, because the load is sitting right down on the top of the cell, we build them up to 100 tons in the sanitary. You have to choose the accuracy level that you're looking for. We range all the way from 2%, which is a little less accurate, all the way down to 0.025% of full scale. It's important you understand there are some things to think about with accuracy. In a conventional, somebody just asked me a question. Bear with me for a moment. Let's see. Somebody's asking how hard it is to calibrate these systems. I would tell you this, it's an extremely simple calibration with them. That's a little beyond the scope of what we're going to do today. I think we're going to run another seminar down the road where we're going to go into some more detail with the display. But for today's purpose, just understand it's about a 3-step process. It's very similar to what you do with a strain gauge cell. They're not that much different. okay? Again, go back to the accuracy here. So you've got weight or accuracy ranges you can pick from, and these are also very common to what you would see for accuracy ranges with a strain gauge. However, there's a couple of things to think about. There's a difference between accuracy and resolution. And our load cells are certified or can be certified as accurate as OIML level 6, which is a super high accuracy and is among like the highest accuracy strain gauge load cell you can get. We can match that. However, our resolution can be up to 3 times better than a strain gauge cell. What does that mean? Think about when you step on your bathroom scale. You might have a scale that shows 1 pound increments. You might have a digital scale that shows 1/10 of a pound increments. That's resolution. So if you have a 200-pound scale and it will show 1 pound increments, that's 200 divisions that the scale can perform. That's the resolution of the scale. Depending upon the application or what we're doing and how strong the installation is, we have installations that can measure up above 10 and 12,000 divisions. So you can't do that with a strain gauge system. So think about that. That can help you be more accurate in your measurement. Back to how you select. So you got to think about how many legs you're going to support. It could be 3, it could be 4. In some cases, people support 1 leg, and you can do that and measure with dummy load cells. You have to think about what the communication you want out of it is. The actual display can produce a 4 to 20 milliamp out, or it can communicate on a Profinet, Profibus, DP, DeviceNet, Ethernet IP, Modbus, TCP. Those are all communication protocols that we can provide. And we have calibration certs. If you're considering a compression style load cell, these are some things that people like about them. They're designed according to EHEDGE guidelines. These radiuses are made to meet their requirements. There's no bacterial traps in here, and that's important. You may see a strain gauge load cell that has a similar look to it, where you see this button in the middle. But a lot of them, this button is a separate piece and sits down inside of a well inside the cell. And that well can be a bacterial trap. We don't have that. This is an absolute smooth surface. The entire surface deflects under load. You can see a typical installation right here. You can imagine this is a mezzanine. This tank is sitting down inside of a mezzanine. And this might be a 3-point system, I believe. But it's as simple as setting the tank right on top of the load cell. I'll show you a little more about that in a minute. This beam load cell, again, the system is capable through 4,000 kilograms. That would be a 4.1,000 kilogram system. Again, same kind of accuracies, same decision about supporting points, same electrical outputs available, same calibration, okay? Again, it's going to be a function of the installation and the load that's going to dictate which way you're going to go. Here's an example of a tank sitting on a beam style load cell, excuse me. You're going to notice, if you look at this picture, this is an older style that we had before we moved to the new streamlined bellows. This one had a little bit of a busier bellows, and people didn't like it because it's difficult to clean. This unit is much easier to clean and much more sanitary. We've gone to that about 2 years ago. But you can see the same thing here. Here, this tank is sitting on a frame. Here's one load cell. There's another one here, and there's probably a third on the back. I'm sure there's a third on the back. And as that beam deflects, we're able to measure the load. And there's an Alpha Laval seat valve on the top of that tank. This is a little bit of a different animal. This is called a single point load cell, and this is used in scale applications. Lower capacities down between 5 and 150 kilograms, higher accuracies. But the real interesting part about this cell is it's designed with a more robust body to be able to accept off-centered loads. So this is the typical installation where you'd have that in the middle. You could offset loads to any one of these corners, and this would remain accurate, where other styles wouldn't be able to handle that degree of offset. So these are designed specifically for scales. So think about the other things to consider here, and we can kind of move through this relatively quickly, but these systems run on 24-volt DC, and they require very little power. It's minimum a 2-amp power supply. We can provide a 110-volt converter in the enclosure. We do it routinely, so if you want to plug it into the wall, you can. And again, these are some considerations. You need the output module, which is that weighing module. You need one of those per system. And you got to be sure that the BNC connectors are mounted correctly on your wiring. This is just an example of a different weighing module with 4 inputs. This particular weighing module can be used without a display if you want to integrate this directly into a PLC. You can do that and not require a display. You lose some functionality of the system, but OEMs sometimes use this because it's a little more cost competitive. So again, this is that hygienic system thing. I think this slide's a little out of place, and I apologize, but you can envision here they need a mounting kit. They've got to keep this thing aligned and on top. We don't. How do you keep your load on top of this system? I'm going to jump a little bit here and show you something. This is as simple as it is. If you look at this drawing here, all we need to have is a leg on the tank that's capable of centering itself over the button on the load cell. You'll see that one that we looked at where the tank was sitting down through the mezzanine. This would be an example of where that leg came off the side of the tank, and there's nothing more than a centering ring sitting on top of our load cell. That's all you need. You don't need to have any other way to stabilize the load cell. One thing you do have to think about, though, is you got to consider that you've given enough clearance between the button and the ring so that the load cell, the tank, can move thermally. What does that mean? If I've got a tank that's 10 feet in diameter and I raise the temperature 100 degrees, the tank's going to grow. And you need to be able, the tank needs to be able to move on top of that load cell in a way that it doesn't bind up. So those are some considerations you need to think about, okay? I'm going to back up here and see what, there we go, back to installation. In a perfect installation, we do want to try to make sure that the force is applied as vertically as we can, and we want to keep the load cells as far outboard on the load as possible. What's that mean? If I've got a square tank, I want the load cells as close to the corner as I can, the actual weighing portion of the load cell. I don't want them in the middle of the tank, all right? And remember, we got to maintain some tolerance around there for expansion and contraction, all right? One of the things you do have to think about is, I just told you, you don't need any way to mechanically support our load cell. That's true. But one thing you do have to think about is if you've got a tank outside or in a place where it might lift off, think about a big grain silo. If it could tip over and fall off, you need to have some sort of mechanical restraint on it. Our restraint is not as difficult to deal with as a strain gauge because we're only using it to stop the tank from tipping over. We use big holes in the legs here where the bolts go through so that they don't bind up. We leave plenty of room in the nuts so that it doesn't stop the unit from reading accurately. It's only there for a catastrophic situation. And you can see what I'm talking about here. Okay. One of the other things we think about in installation, and again, we can go further into depth in the next presentation, but we got to think about how we connect our load to the process lines. One of the things that is true of anybody's load cell system, whether it's mine or anyone else's, is that the load needs to be able to move. If you bind the load up and it can't move, then you can't measure it. So you got to think about rigid piping. That's a no-no. You need flex joints. You got to think about ways to allow the tank to move. Where's the last place I'm going to support the piping? How far away from the tank so that the tank doesn't bind? Those are important things that we can help you with. If you change plane coming up to a tank, in other words, come this way, put a 90 and come back, it helps the tank to move. If you do multiple plane changes, it's an even better thing for bigger diameter pipes. Okay? So I'm not going to go too much further into the specifics of the cell for today, but what I do want people to be aware of, again, is that the physical method that we measure is different with an Alfa Laval capacitive unit. We're not bending the sensing mechanism. We're not subjecting it to loads, to side loads, to torsional loads. We're allowing it to do what it's meant to do, which is measure. We're not making it be a structural element of the cell. And I'll tell you, we have had clients that have been fighting with strain gauge systems and the related support equipment for years. In our business, we're finding that in mobile tote applications, mobile mixing applications, this is a home run. We're also finding that we even have clients that have fixed tanks that were having trouble every time they flipped the lid open on the tank. It would bind up the load cell mounting kit. We put these systems in and we've solved the problem. I'm glad that you've taken the time to learn a little bit more about this with us today. I'm happy to talk to anybody further in depth, and our contact information will be on the presentation when we send it out. You can also find us on YouTube. You'll be able to search on capacitive load cells and find this presentation. And hopefully you've learned a little something today, and we'll have a chance to interact with you in the future. Thanks again. Bye-bye.